Once we've imported the data and prepared it to be ready to work with, we have to examine the data and try and understand if we have good data, if there are errors or what we might call anomalies in the data. So in this video, I'm going to walk you through some simple techniques for identifying outliers or anomalies or errors. After identifying those, we'll do a few things to deal with them. But a lot of the errors and the anomalies and the outliers will depend on the data set that you're working with and whether you can definitively identify errors or not. So this is a new data set. I'm going to use these packages that we've already used in the past, and there are two data sets here. One is annual financial information from a large set of companies, and another is a data set that has indicators for whether a company in that year had a fraud, or at least whether the SEC identified the company as having a fraud. So we have here the annual financial statement data, so I'll walk through this really quickly. GV key is an identifier for company, so each identifier is a different company, fiscal year, and then the data date. This is the end of their fiscal year. Then NI is net income, accrual, ACC is accruals, or the difference between net income and cash flows. So on a reconciliation using the indirect method, then this would be the sum of all the adjustments that get made when you're reconciling net income to cash flows. AT is total assets. RevT is revenue, total revenues. PP&E net, so this is the net property, plant, and equipment. And notice we have lots of different companies, lots of different years if we look down for a ways, and then these annual financial information. Then in this second data set, we have a company identifier, which comes from the SEC. We have the other company identifier over here, the GV key, that will allow us to match to the other data set. And all of these ones say that these ones were identified as having fraud, or rather having restatements that are related to fraud. And then this res begin date is the restatement beginning date. This is the restatement ending date. The interesting thing about this is we want to match the yes, there is a fraud during that time to any time between these restatement dates. So here there were 4 years, so then we want to be able to, well, I guess 5 years, we want to be able to match it to all of those years. So that creates a slightly different merge than we've had before. So we're going to merge this first data set to this second data set, and really we're taking data set 2, the fraud one, putting it onto every observation in data set 1 where there is a match, and it's going to be matched by the same GV key. And then this is the reason we need SQL. We're going to match where the fiscal year end date is any time between the beginning restatement date and the ending restatement date. This means that that fraud indicator for a company that has fraud occurring for multiple years then will match on multiple times. So we merge that. This next part is also new, so we have this, I'm setting any missing fraud values to 0. That means we only matched on and the ones that show up say 1, so we want to fill in where it didn't say 1. And this is a different syntax than you've seen before. So this is looking at the data frame DTA that we just created and the column fraud. And then the square brackets, what that does is say we're looking at this column, but this tells us which rows to look at within that column. And so this says if is.na, that means is it missing? So if it is missing DTA fraud, so anywhere that this column has missing rows, set it to 0. So then when we open up this data set, you will see fraud is filled in 0. And then, if you keep looking somewhere in here, there's a 1, we can sort it and see that there are some 1s in here. Then I'm writing this out to a new CSV file. The reason for that is so that I can use it in KNIME and not have to do these merges in KNIME. We saw that we could do the merges in KNIME, but I'd rather do it here because it's a little easier, and then I'll go through the other stuff in the KNIME software as well. All right, so we've done some of this before. We're going to create some new variables, sort by company and year. I'm going to group by company. That's because I'm going to use a lag function here. And then at the end, I'm going to ungroup. And then let me walk through the variables that I'm going to create. So one is ROA. This is net income divided by the prior year's asset. So it's going to go up a row. Well, because that is sorted by year, company and year, then that is last year's ROA, or last year's asset. So it'll create ROA each year using net income divided by the prior year's assets. Accruals, the same thing, net income minus cash flows divided by this. Change in ROA, that means this one I'm going to take ROA minus the prior year's ROA, accruals minus the prior year's accruals. And then because I want to look at this lagged assets, I'm going to create a new column that is the lag assets. I'm just calling it AT_lag1. Then for our own interest, here are the other variables that I probably would look at some point. So run all of this. Of course, we would go in and check once it runs. So this one takes just a couple seconds longer, well, more than a couple seconds, because it's a larger data set doing a lot of lags. And we can look in here and make sure. So these ones are not available because there was no prior year to do the lagged assets. Now we're missing 2 years here because we did the change variable, and same thing here. So looks good. Then what I'm going to do for the rest of this video is focus primarily on this accruals measure. The reason for this is accruals, so the difference between net income and cash flows is often used as something like a red flag for fraud or manipulation. So we talk about it in lots of classes that if accruals or if net income is largely different than cash flows, then it's something to raise a flag about and to worry about. So I'm going to use this as the one that I would look at to try and understand errors and outliers. However, if you're going to use this data, let's say you wanted to go do some sort of model with these variables, you need to look at every variable and try and understand what's happening with every variable. So let's do accruals first. So we've done the summary function before. Let's look at what comes out of this. So accruals, remember, is net income minus cash flows divided by assets. So assets in general, we might expect to be larger than net income. So because of that, we generally expect accruals to be less than 1 or greater than -1. So somewhere a fraction that's smaller than 1. If it's not, then that means the income numbers are larger than the assets, or at least the assets from the prior year. So that raises some questions for us. So we look down here, on average, the median is -0.5. The mean is slightly larger. Slightly larger negative, and you'll see why. This minimum is very, very large negative, and the maximum is very, very large positive, not quite as large as the negative. So that means we have something that seems suspicious. Really what ends up happening is there are some with very small assets that is driving some of this, so we'll deal with some of that in a minute. And there are a bunch of missing values. So at some point we might have to deal with those missing values. I'll show you some of the adjustments to the functions that we have to do to deal with that as well. So this raises some questions. Are these errors? So you could go and look at each of these very extreme values and look at the errors. Or it could be just a function of the ratio that we have, but either way we have some big extremes that seem suspicious to us. So another way to look at it, we could look at the quantiles. So the quantiles would be the percentiles of the distribution. And here I just want to look at the extremes. So I'm going to look at the 0.1%, so the smallest fraction, then 1%, 5%, 10%. And similarly on the high side, 90, 95th, 99th, and 99.9 percentile. And what this does is let us look at the very extremes. So when we look here, we see the minimum is very, very large. Even at the 0.1%, it's much smaller, so minus 49. That's still maybe suspicious, but it seems much more reasonable. And then same thing, it's once we get to the 5th percentile, we're in a fraction that's less than 1. And same thing on this side, although the extremes are more on the left. So another way to look at it, we're going to start this plotting package. ggplot2, we'll use it for most of our plotting. And we can do this without ggplot2, at least some of these things, but it creates a framework that allows us to do the same sort of thing every plot that we use. So the package, what it requires us to do is when we create the plot, so this ggplot function creates the data for the plot. It doesn't actually do the plot, but creates the data for the plot. And you first have to tell it which data frame. So here it's the temp data frame. And then AES is what it tells it what goes into the plot. So AES X equals accruals, so that we're going to use this accruals column. So notice we set it up the same here and here, even though these are different plots. And we set it up almost the same here. This one, it has to say sample equals accruals instead of X. That's because of the particular plot that we're using. So then what comes different here is once we tell it which data to do, anytime we want to do something different, we do plus. That says add something to the plot. So here we're adding a histogram, and the function is geom histogram. Then we're going to also add, and this is a theme that it creates a certain template for the histogram. And we can use this theme classic on everything that we're going to use. For the histogram, we don't need to put these other things here in the middle. This just helps choosing the format of the graph. So I'm going to tell it to do the lines as black, filling in as gray. Alpha is how transparent to make the well, I forgot what it does. I can't remember if it's the making it more transparent or separating, but it makes it look a little nicer. And then we're going to do the same thing with these other plots. This one is a box plot. So what we're looking for is the box and whisker plot. That'll do this. And then this is a quantile plot. And we have to do this first because it has to figure it out. And then this one creates a line that goes through it to show us what the normal line would be. So let's run this one first. This is the histogram. And it comes up over here on the bottom right. We can zoom in, make it larger if we want. And this doesn't look like a histogram you might be sort of familiar with seeing. And that is because most of the observations are here near 0. And then we have some very large ones out here that we can't see. So remember, we already saw that there's an extreme negative value. Well, it's way out here, and it's only one of those, so it doesn't even show up on the graph. And so this is not really usable. So anytime you see a picture like this, either you have something you don't expect, or you have something very extreme that is not allowing you to see what the bulk of the data look like. So in other words, this is an outlier. or there is an outlier here that we can't really observe. So this is not a desirable looking histogram in terms of what we would like to work with in terms of data. So we'll come back to that in a little bit. Now this box plot, we'll do the same sort of thing. And so it has some warnings. It says we have some non-finite values. That means we have some that are infinite in there. And that's because we're dividing by 0. So that, luckily, it removes this for us. And we go look over here. This shows us that almost all of the observations are here around 0. But there are some outliers. So getting away from the bulk of the distribution, we have a number of outliers to the left, and the really huge one that is causing us problems is way out here, and we have a few to the right as well. So this, we can't even see the box, it should be around here, and that's because of these large outliers. So again, we have multiple ways to look at it and see something really extreme is going on with some of the values. And this quantile-quantile regression, quantile-quantile plot, takes a little longer because it has to calculate those quantiles, and then it has to plot it, so it takes a little while again. So once it pops up, then we can zoom in and look at it. There we go. So the main reason this takes forever is that it plots every single one of these dots along the way here, and that's 200,000 dots. So it takes a little while to run this type of a plot with large data. So this here tells us on the line, this is, if the dots are on the line, that means it's very similar to the normal distribution. As we get out here, this means there are more positive values that are away from the distribution. Same thing with the negative ones, and again, we have some that are very far away from a normal distribution. So again, this sort of shows us there are some problems going on here. So the sort of ideal situation, if we hoped that our data was normally distributed, would be that it's more or less on this line. So all of these tell us there are some outliers, some potential problems in the data. The problem is these really extreme ones, we don't know the cause of those outliers, what's going on with the data. So if they were actual errors, then we should fix those errors or get rid of the errors, because that messes up our data. In all of the analyses that we might do, having outliers can cause problems. In other words, the results will be driven by those outliers, and so because we would like to make inferences about most of the data, using the outliers can cause some problems. So we would want to check and maybe remove some of those. So let me walk through a few things that we can do to deal with those. Of course, if we think those are the ones that are fraudulent, then we might try and identify whether these ones are ones or zeros. But there's no reason actually that these ones should be the fraudulent ones. Fraudulent can end up sort of anywhere in here as well. So unfortunately, it doesn't help us identify the actual fraud very well, but it does help us identify problematic things in the data. So let's go through a couple of things that we can do. So the first one, we can try and alter the sample. So something that is causing these errors or outliers, whatever they are, we could remove those sort of from the sample. So dividing by assets creates a potential problem. So if we have very, very small assets, that creates very extreme values. And it's only because of the denominator, our choice to divide by assets, that is causing that problem. So one thing we can do is get rid of those very small companies. So we could look and see what the distribution of these assets looks like. So notice at I should have done this first one. So we have some with 0 assets, total assets. That seems problematic. or at least the prior year. So some of that is coming from data where they have 0 assets the prior year and then they start activities, so it's sort of a strange thing to divide by the assets, so we could get rid of those. We could also change our measure, but that's not something we will deal with here. And even if we look at the extreme quantiles, notice we have decimal places, so these are in millions, so we have some with thousands in assets instead of millions, and all the way up to 1%, we're still less than 1, so we have things that are causing problems. So let's say we're going to require that our sample only deal with companies that had at least 5 million in assets in the prior year. Given that these companies are large public companies, that's not a very large cutoff. Then we can go through and see what that did to the outliers. So go here. All right, so here we have the quantile plot. Notice again, it's mostly flat in the middle, and we still have these extremes on the outside, but they're fairly similar on the positive and the negative side, and they're not nearly as far away as they were before. So we could look at the histogram. Notice we still don't see a lot of the distribution. That's because we are still far. There are still some that are way out here, very far beyond the rest of the distribution. At some point, you'll see this is much closer to a normal distribution than we're seeing right now. But at least we can start to see something to the distribution. And we can do the same thing with the box plot. Notice we're closer in, but still the same problem. We don't see the main part of the distribution. So that didn't solve everything. It solved a little bit of the extremes, but not everything. So the next thing we could do is remove some outliers. So I'm going to create a cutoff for the bottom and a cutoff for the top. So I'm going to take the quantile, the 2 percentile, and calculate that. So here it says minus 1.137. And on the positive, I'm going to do the same thing, 98th percentile, 0.344. So this is saying if we cut the distribution off at the 2nd percentile and the 98th percentile, we're going to set that equal to the low cutoff and the high cutoff. Something I forgot to mention before, if we don't remove missing values, so this comma na.rm equals true says to true, remove missing values. NA are missing values, RM is remove. So when we're calculating the quantiles, remove missing values. And it won't work if you don't do this, and there are other functions when you're trying to calculate a mean or something like that. If you don't remove those, it will cause problems. So we're going to run these, create a high and a low cutoff. We're going to use that to cut off those extremes out here. Okay, so we create a new data set from temp. Filter is a function for keeping only rows that meet this criteria. So we're going to filter out rows, or filter keeping rows that are between the low cutoff and the high cutoff for this accrual column. So that we are only keeping rows where that accrual column is between these 2 points. Now our data set's going to be slightly smaller, so we look and see, let's see, we're doing temp 2. We went from 248,000 down to 214,000, so we lost 30,000 rows during that. So given that we have a large set of data, that isn't too large, but we also lose data, so that's also not good. All right, so then we do this summary, look and notice now we're between these 2 extremes. And we can go through and do all of these plots as well. Let me just do this histogram one. And you'll see now suddenly it looks like we have a semi-normal distribution, something that we can recognize in the data. So this was hidden because we had extremes that were so far out to each tail. Whether this is the correct thing to do or not, that's a great question, but it removes the effects of those extreme outliers. There are other things we can do here as well, but we're just sort of getting started. Another thing we can do is, if there is a variable that creates some problems, we can do what is called a variable transformation. And that is something that keeps the order the same, but pushes in extremes. So if it's a variable that is all positive values, then we can use the natural log. That's really common. So let me show you this asset. So let's say we're looking at this asset column, and we see it has very, very large values as well as some small values. Well, if we were to plot that histogram, we can look and see at this histogram. You'll see it also has these really large extreme values to the right. And we can't even see that they're there because they're so large. Well, we could take a natural log, and I'm adding 1 to that because we have 0 values here. We do the natural log of assets, and what the natural log does is take these extremes and push them in closer to the rest. We plot this one, and now it looks pretty much like a normal distribution, and again, that's because it's taking the very large extremes and pushing them in. The very smallest ones get pushed up just a little bit, so it's smashing the distribution together. That doesn't work with the accruals column because we have negative values as well as positive values. So if we wanted to transform that column, we'd have to think of some other options as well. All right, this seems like a lot for you to get working with. And in practice, you have to do this on any variable that you are thinking about. You may wonder about which thing to try, right? Do we alter the sample, remove the outliers, do some transformation? Unfortunately, there is no rule of what you can do, so most of the time we would try multiple things and see if our results are different when we do different things. But we have to look at all of the data every time before we start things, because how the data looks can affect our results.